Greetings. I want to talk to you for a little bit about the results of the lab, the Impulse Momentum Lab, which is Unit 8A2, relating impulse to momentum change. It was a little bit rushed. We went over the results at the very end of whatever it was, Friday, last class. And what we saw in general, when we looked at everybody's data, we're going to make that an impulse, is that whatever momentum change you measured using the velocity graph, it was equaled the impulse. So the momentum change, this was the hard stop. No, this was the jerk. They were the same. This was the not so jerk. Whatever the impulse was, it caused a certain change momentum. This was the hard stop with the string. There was a certain impulse associated with that, and that matched, in theory, exactly the change in momentum of the object. And the last one was the bungee stop, and there was a certain impulse associated with that, and that caused a change in momentum. So the big idea is that an impulse on an object will result in a change in momentum on the object. So I guess that is the absolute big idea, is that impulse causes change in momentum of the object. These are vectors, but because we're only going to deal with one-dimensional motion, all x, generally, maybe sometimes y, then we can just say I equals delta p, and we're going to use plus and minus for our direction. So even though they're going to continue to be vector quantities, we're not going to probably use the vector hat so much, because the vector aspects can be totally supported by using plus for positive direction and minus for negative direction. Okay, so let's put this into action. Suppose an object of unknown mass receives an impulse of 50 Newton seconds. What's the change in the object's momentum? This is where I usually begin to talk about Napoleon's white horse. Like, what was the color of Napoleon's white horse? Well, you say, well, you kind of said already it's white. And who is buried in Grant's tomb? Grant. Well, you kind of already said Grant's buried in Grant's tomb. Well, the whole idea then is, if an object receives an impulse of 50 Newton seconds, what is the change in the object's momentum? Well, it's going to be 50 kilogram meters per second. So if I equals 50 Newton seconds, then it follows, it must be that the change in momentum then is going to be 50 kilogram meters per second. Let's take a little pause there and look at these units, because if we're saying that impulse equals change in momentum, just like an apple must equal an apple and a banana equals a banana, you can't say an apple equals a banana. They're not the same things. Then these two things must be the same thing. So let me just write the units here. We have, no, not 50, a Newton second for the units. And what we're saying then is that the units of Newton second must equal units of kilogram meters per second, even though they are completely different in appearance. But let's remind ourselves of what is hiding in this Newton. It is a kilogram accelerating at a meter per second squared times a second. I think you're already seeing it now. Kilogram meter per second. And that is true. The second on top and the second squared on the bottom partially cancel, and we're left with kilogram meter per second does in fact equal a kilogram meter per second. So even though when we're talking about impulse, we typically say Newton seconds of impulse, and even though when we're talking about momentum, we usually say kilogram meter per second of momentum, they are exactly the same. So we could use them interchangeably. But again, traditionally we say Newton seconds for impulse, kilogram meters per second for momentum, but you could swap them back and forth. They are exactly the same thing. Okay, let's go back to this guy. What impulse is necessary to cause a change in momentum of 100 kilogram seconds? Who's buried in Grant's tomb? Grant. So if impulse equals delta P, and we want 100 kilogram meters per second of this, what am I doing here? Well, then 100 Newton seconds of impulse is what's going to get you 100 kilogram meters per second change in the momentum. We'll stop there.